Hi, everyone. This is Kenny Lee, and let's talk a little bit about light, color, and just a touch about vision. So, first, talking about light. Light's part of the electromagnetic spectrum. And I've got the electromagnetic spectrum down here. We got radio waves, microwaves, infrared, that's IR, visible light, ultraviolet, UV, X rays, and gamma rays. Now, when we look at the electromagnetic spectrum, over here with radio waves, over here on this side, the way I've got it set up is radio waves. This is the end of the spectrum that has a long wavelength, low frequency, low energy because of E equals HF. Over towards the gamma ray side, that's when you have high energy, shorter wavelengths, and much higher energies. Same thing, anything towards the left-hand side, the way I've got things set up, you have these low frequencies, long wavelength, low energy. Towards the violet side or a gamma ray side, you have higher frequency, shorter wavelength, higher energies. And so if we can compare green light to blue light has a higher energy, green light has lower energy, green light has a long wavelength, blue will have a short wavelength. And a way you can remember that is think about, let's say you've got a basketball team, got a new recruit named Red because he's got red hair and he's like 7'4" or something like that, tall, skinny guy. And so when he walks, he takes very long steps. Okay, so long steps means long wavelength. Let's say he's dating like a cheerleader named Violet. Okay, she's only about 5'2". Okay, and so if they go to class walking hand in hand, he takes these big long steps. She has to take a bunch of short steps to keep up. So if you keep that analogy, long steps for red, long wavelength, doesn't have to take very many, so low frequency. Violet has to take a bunch of steps, so high frequency, and her steps are really short, so a short wavelength. And from my experience, tall people are kind of lazy, so red has low energy. Violet is a cheerleader, bouncing all over the place. She's going to have a lot of high energy. She's going to have a lot of energy. So you can use that analogy to kind of remember what side of the spectrum has low energy and what side of the spectrum has high energy, high frequency versus low frequency, long wavelength versus short wavelength. Now, to get to more into spectrums, different elements give off different set of wavelengths, different photons, depending on what element they are. Each element has its own unique kind of fingerprint. And so we're going to take a look at some of those and see what they look like, as well as having more of a stylized view that's a lot cleaner than you'll get in the demonstration. Let's take a look at this neon light. See, it's a nice red color, but watch when I put a diffraction gradient in front of the camera. All right, let's take a look more at the light that's over this one right here. If I can get this to zoom a little bit more. We may have some focusing problems with my camera. I may have to put a still up. But that's neon with the diffraction gradient acting like a prism to break the light up into the different colors of the rainbow. Okay, this one's helium. There we go. So, if we look out, that one should be helium. Again, the spectrum repeats. So look between red and blue. Hydrogen. This one is mercury. This is what the spectrum should have looked like if I had a better setup, a darker room, and a better camera. There are 3 different primary colors of light. Now, this may be different than what you learn in art class because they talk more about pigments, but we're talking about actually mixing light. And so the 3 primary colors of light are red, blue, and green. Although in art, you'll learn red, blue, and yellow, but again, those are primary pigments. They are subtracting light, they're taking light out. So a blue object, you hit white light onto that blue object, it absorbs all the other colors, but let's say blue, and so it looks blue to you. So paints are subtracting colors out. We're going to add colors. So we're talking about a beam of blue light and a beam of red light, and a beam of green light mixing together. And if we do that, we actually get white. So if we mix red light plus blue light plus green light, we get white. That goes a little bit on how our eyes are designed, but we can make up every color that we can see from those 3. Now, what if we just mix red and blue light together? Well, the color that we actually get out of that is a color called magenta. If we mix red and green light together, we actually get yellow. Can't see that very well. Let me change this. There we go. Just for this one, so you can see that yellow is there. Now, if we mix blue and green light together, we're going to get a color known as cyan. Let me change the background back a little bit. So we get, let's go there. There we go. So red and blue light makes magenta. Red and green light makes yellow. And blue and green light makes cyan. Now, if you got a color printer, most likely you don't have a red cartridge, a blue cartridge, and a green cartridge. What you usually have is magenta, yellow, and cyan. Because again, we're adding pigments, taking away colors, but those are light enough colors that they're a lot less harsh than trying to use a red, a blue, and a yellow in the color printer. Let's take a look at this electric crystal. So if I turn it on, what do you see? Let's look at it in the dark. So if you just stare at it, it looks like it's white. Or depending on the frame rate of my camera, it may look a little bit different. But if I move it to the side, you can see it's actually 3 different LEDs. A blue, a green, and a red, flashing one after the other. Our eyes hold on to the image, so our eyes mix the colors together and we see white. Or we should, again, depending on the resolution of my camera. But if it's separated, you can actually see them go off one after the other. Right. Now for some more demonstrations about light and color. The human eye can only pick up 3 different colors, red, blue, and green. And it's a combination of those colors that gives us all the colors of the rainbow that we see. I've got 2 slide projectors. And in those slide projectors, I have colored films that I can put in there. So when I turn this on, it puts that color up on the board. Well, if I do 2 different ones, so I add the green one to this side. Now let me turn off the light. I've got a red and a blue. And I don't know how well this will capture on that camera, but when I combine them, they form yellow. And the neat thing is I can create different color shadows depending on which color I'm blocking. So I create there we go. Now if I change one of them, so let's say Instead of green, I use blue. Now we've got magenta, where the two overlap, and we get magenta. And my camera's struggling to keep up in the low light. So let's try green. And there's cyan. If I get close enough for it to make the details out. Oops, too far. Let's merge them just a little bit. There we go. And there's cyan. Again, depending on which one I block, I can create different color shadows. All right. Now, if I could combine all three, the red light, the blue light, and the green light, I should get white. So the very center is white. I don't have three projectors, so I can't do that, but that's what would happen. Hi, this is Kenny Lee, and I have got an overhead projector here. On top of it, I put this polarizing film, and this stuff is mica. Now, the neat thing about mica is it's bifringent, which means that light, because light's going to go through that polarizer, that means it's all the light is vibrating in one direction. Okay, so let's say all up and down, nothing left and right. Then that light goes through here, and since this is white light, it has all the different colors of the rainbow. But what mica does is it's bifringent, which means that as the light passes through the material, light of different wavelengths gets rotated different amounts, depending on the thickness of the mica. And so that means that the color can change when I add this other polarizing film. So you can kind of see a little bit there. I'm going to project it onto the screen in front of my room, right there. Let me fasten this in place so you can see it. There we go. Zoom in a little. And then watch what happens when I put this other piece of polarizer over the top. And as I turn it, the colors change depending on what color is corresponding to how that top polarizer is aligned. So if I turn it this way, so you can actually see as I turn this that the color changes. There's where the polarizers are pretty much at right angles to each other. And here's where they're pretty much aligned. But the color changes. Okay? So, white light contains all the colors of the rainbow, and we can pick out different ones as we see fit. All right? But that material mica is bifringent. How does the eye work? Well, the eye is really kind of neat. It's like what we call a pinhole camera almost, where we've got a couple of parts here. We got the pupil, that's the opening that lets the light into the eye. And then you got the lens, that's the cornea here. I want to show you a better picture than what I drew here in a second. And then the iris is the kind of colored part of the eye. And then you got inside here, there's kind of a clear jelly-like substance called the vitreous humor. And then you have the retina, which is basically the screen that your eye, the lens and the cornea, project the image of the world onto the back of your retina. And that's picked up by different cells. You got two different types of cells. You got rods, which are basically your black and white vision. They're very light sensitive. You really only use them in low light situations. Then you have your cones. Cones come in three different flavors. You've got blue, red, and green. So we only see blue, red, and green, or a mixture of those, and of course the absence of light, in order to see all the different colors that we can see. Matter of fact, your computers and your phone screens and stuff like that, all the colors you see from them are all made up of red, blue, and green in different amounts, in different quantities. And so that image projected onto the back of your retina, fun fact, this image is actually upside down. Your brain flips it right side up. But the rods and cones acts like little detectors that collect that information, send it through the optic nerve, and your brain puts together the image that you see. If you're deficient in one of those sets of cones, let's say you're deficient in red, okay? A lot of times we call this color blindness, though it's not necessarily red. There's 3 different types, one for deficiency in each different color cone. Let's say you're deficient in red and you look at something that's red. Well, it won't be invisible to you. So color blindness doesn't mean that, like, if I'm red colorblind, if somebody's dressed in red, they're invisible to me. No. What that means is that I won't see that as red. I may see it as a brown or something similar to that. But it will be a color. It just won't be the same as what everybody else sees. You'll get an image slightly different, and you simply won't know unless you've done a color blindness test and where somebody tells you that what you're seeing is not what everybody else is seeing. So let's take a little bit better look at the eye. Here's a much better image of the eye. And so it lists all the parts, but basically it's the same thing as I just drew.